Hey everyone, today I want to show you this really cool tool that I made. Um, it is a way to visualize the derivative as the slope of the tangent line. So what it does, let's scroll down so you can see this slider bar. So what it does is it allows you to drag this slider bar that moves the time, and everywhere for whatever time you have selected, you can trace that straight up, and for whatever time you have selected, it will find the slope of the tangent line for you. It will draw the tangent line for you, find the slope given here and also given up there. And then you can trace that down, and that slope value becomes the y value, the value of the function down here. This is whatever function you chose. I just chose to call it f of t. And then this function, so this graph is f of t, and this graph is the derivative of that graph. So every point along this graph is the derivative of every point, the same time. That's why the red dashed line connects them, pink. It connects the two graphs and also with the slider bar so you know where the time is. So all of those are the same time. So at this time, that's the value of the slope. Let me see if I can read it here. 13.92. And then you trace down that dashed red line, trace it over to the side, and you see that 13.92 is represented right there. So you can play with that as much as you like. It is an HTML file right now, so it's on the web. It's a web page. I will put a link to it in the longer form video in the description. So what you can see here in the top graph, this is a generic f of t. I chose to call it f of t because it could take the place of either position versus time or velocity versus time. If it's position versus time, then when you take the derivative, you get velocity. And if it's velocity up here, when you take the derivative, you get acceleration. If you aren't that far yet, then maybe you want to hold off on this until you've gotten to the definitions of velocity and acceleration. There is, up at the top here, if you want the units to match, it's totally optional. You don't have to enter the units. But if you want the units to match, there is a place up here to add units. So if you're thinking that it's position, you can type an M up there and then hit return, and then it will populate down here in all the places where you need to see it. So you can see that the value of f of t is now, I'm thinking x of t myself, and now you can see that that has a meters unit with it, and then the units for the slope up here also get the meters per second, and it fixes the axis labels. So up here on the top where it's the function, you get meters, and down here where it's the derivative, you get meters per second. So again, that works if you're thinking that it's a graph of position. And you can play, like I said, you can play with this slider bar, and if you want to, you can change the function, and you can also change the limits of the function. So, so up here, up at the top here, there I have the function typed in for you, and I have several presets. There might be other functions. You might recognize the cosine. So there's a function of the cosine at the top. And then it is the sine at the bottom, but you don't have to know that if you've never seen that before. So it starts at 0 here on this axis, or sorry, on the time, in the time dimension, there's the 0 down there. So the cosine starts at the amplitude as you expect, goes down to negative amplitude, goes back up in an even cycle. Then if you drag the slider bar for this particular graph, you will see the graph on the bottom is what gets mapped out. Look at the computer. So when you start over here at 0, at t equals 0, the slope of the top graph has a value, and indeed the slope of the value, that value appears down here. As you sweep through, you can see all those values being traced out on the two graphs. So I'm super excited about this. I think it's really cool. I mentioned I have all these preset functions that I coded in for you. I might add a few more there. I don't know. I'll be interested to see if people leave me any comments. I'd be happy to take requests of things you want added there. One of the reasons I added things is so that you can see how it looks. Oh, so I have the cosine here. And you see in the preset, so in the preset there, it looks like a nice symbolic cosine of 2 pi t. And then when you look up there at what you have to type, you actually have to type the asterisk for the multiplication symbol. So to get 2 times pi, you write 2 asterisk pi for pi, and then another asterisk for multiplied times t. So some of the reason for choosing some of the presets is just so you could see what the functions look like. So you can see what to type if you want a cosine function. That's probably enough that you can guess, although there's also a sign in the presets. Oh, there's no tangent in the presets, but you can probably guess it's just tan, T-A-N, and then parentheses of t if you just want plain t. So there's all those presets where you can see an example of what to type. And the reason you need an example of what to type is it is completely set up so that you can make up your own function. So you can go back up here, choose one that you might think it's the closest to what you want to do. This happens to be one for projectile motion. It's rounded. If you know anything about projectile motion, the acceleration due to gravity is 9.8 meters per second squared straight down. And then there's a 1/2 in the equation, so I rounded 9.8 up to 10 and then divided by 2 to get that 5 there. So, so that's an example of one with an initial velocity that would correspond to 30 meters per second straight up into the air. But that's a really high number, and maybe you have something where you only drop it from a 1 meter height, for example, and you want to see what that looks like. Those numbers, because it goes so high, dropping it from a 1 meter height is like dropping something from the height of the table to the ground-ish. And that is way too long of a time for that. So you might be interested, if you're doing this to actually get some realistic numbers, you could change this from 2 to 0.5 seconds. 0.5 is even too long if you're only dropping it from a meter. And you change the plot, and you notice, of course, that the shape doesn't really change very much. It's still half of a quadratic because it started at t equals 0. But now the bottom value there changed, and you can see over there that it's a bit more realistic of a value. Of course, we could solve, if you're that far in your class, you could solve for what the time when it hits the ground would be. Of course, we can eyeball that now that we have the graph. So there you go. As soon as I post the YouTube video, I also will put a link at the bottom of this page, so that you can connect to the YouTube video if you need to rewatch this again to see how to do anything. I think everything's pretty obvious. I guess the one thing I didn't show what it looks like if you're thinking of f of t as velocity. Of course, you can change this to be meters per second. And then, as I mentioned, it should follow that through. And so, yes, you can see up here that you get the function now has units of meters per second, which is exactly what you told it to do. And then the slope has units of meter per second. So you divide by another second. I decided to let it write it that way. You could also often would see meters per second squared as the units for acceleration. And then again, those units are both axes of the graph. Again, the top graph is now we're thinking of it as a velocity and has units of meters per second, and the acceleration has units of meter per second per second. Let me know what you think. There are several other preset functions here. I guess I'll just click through really quickly so you can see a couple of different examples. There's one that has a cubic term. And again, you can do the usual scrolling or sliding the time bar at the bottom to see how the slope changes. And again, everything should track through as we described, so that the tangent line shows up here with the slope, and then we trace the dashed red line down and go over, and we should be able to see the value appear down there. So again, the slope of the tangent line of the function becomes the value of the derivative. A couple other presets that I have up here. So that's the cubic, and we started with the quadratic, and I showed you the cosine already. Oh, here's a natural log. The interesting thing to note about that is that for the natural log, you do have to be careful. You do have to be careful because not every function is defined everywhere. So that the natural log is not defined for negative or even exactly zero. It goes to infinity. So we keep that off of there. So that's another thing that's nice about having the presets for you is there are certain things that are factored in for you so that you don't have to worry about it. Oh, that's a nice one. So just a couple other examples for you all to play with. I hope you have fun playing with it. If there are any requests for preset functions or something breaks, I'd love to know in the comments.